Welcome back. Let us update the case setup here. Right click mesh and update. Next, double click setup to edit the case. In the preprocessor, there is a shell default domain which is the baffle plate. So you can double click shell wall and add this baffle plate to this. Press Ctrl and select baffles. Click OK. Now all the regions are defined. There is no change in the boundary condition. It is same as the previous case. The expressions are same. The output control are same and the solver settings are same. Okay. Only addition is the baffles are added to the shell walls. Okay. We shall go to solver and start the case. Right click solution, edit. We shall not change any settings here. Start run. The case has been started. We shall check the results after a while. The solver has finished. You can see the convergence difference between the previous case and the new case with baffle plates. If you see here, in the current case, the convergence has slightly gone up. This is because baffle plates will lead to a lot of cross flow and the flow may not be smooth as compared to the previous case. That's why the convergence has slightly gone up. This is in the shell domain, but in the tube domain it should be same. We can go here and check. Yes, it is same. There is not much difference here. We shall check the temperature profile. Both the shell side temperature and tube side temperature have converged very well. Okay, let us close this and go to CFD post. Right click results, click edit. The result is loaded. As we have used the previous case, the streamline plots and contours are retained. We can hide the plain one and we can see the streamline properly. We can see here, due to the presence of baffles, a lot of cross flow is happening here, and this is the flow structure. We can turn on baffles, go to mesh region and switch on baffles. We can see here. Next we can switch on the plane. Hide the streamline. Look from top. We can see the temperature rise in the tube region. Next we shall go to the table and find out the parameters. Double click table here. The mass flow on the shell side and tube side are same. The temperature inlet and outlet for shell and tube side are given here. We shall calculate the net heat transfer rate from this data. We can copy this and go to the Excel sheet. This is with baffles. The first one is without baffles. We can calculate the Q value. We shall copy the specific heat here, copy the Q value and paste it here. Similarly, copy the other one. Okay. We can see here, due to the presence of baffles, the heat transfer rate has increased. Initially it was 14.3 kilowatt, now it is 15.9 kilowatt. Okay. Let us calculate the heat transfer rate from the interface from the CFD output. Let us go back to CFD post. Go to calculators, choose function calculator, select area integral of heat flux. We shall choose any of the interface region. Go to the shell to tube side 1, click OK and calculate. Here it is 15,891. Let us copy this. Okay. We shall maximize. The results are matching very well. This is from the temperature difference on the shell side, and this heat transfer rate is from the temperature difference on the tube side. And finally, this is from the interface region heat flux calculation, and this is from CFD. Okay. Next we can repeat the LMTD calculation. This is Kelvin. Okay. We shall copy this again. LMTD has slightly come down. Initially it was 56.8, now it is 56.4. Okay. The heat transfer surface area is same anyway. Okay. We shall calculate the heat transfer coefficient. Okay. Here we can see the heat transfer coefficient has increased with baffles. Originally it was 959 watt per meter square per Kelvin. Now it is 1070.9 watt per meter square per Kelvin. Okay. So we can conclude that with the presence of baffles, the heat transfer rate has increased and also the overall heat transfer coefficient has increased. but the LMTD value has slightly come down. This is because it is compensated by the increase in overall heat transfer coefficient. I hope you would have understood heat exchanger performance calculations from CFD analysis. In the next lecture, we can see analysis of water flow in a duct with heating coil. Okay, thanks for watching this video. I will see you in the next lecture. Thank you.